Find a vector function that represents the curve of intersection of the two surfaces, the cone and the plane. So what might we do first?
Set it as equal.
Yeah, we can set them equal to each other. Or set the, I assume you mean this, equals what? 1 plus x. Find a vector function that represents the curve of intersection of the two surfaces. Are we done?
There you go.
Well, yeah. For first of all, what's it asking for? What type of function?
Vector function.
Is that a vector function?
No.
No. So this is not a vector function. And also, what do we have to be careful about?
T. Well, there's no T.
There's no t in it, right? Does that represent all of the points of intersection?
Yes.
Sure. What else does it represent?
There's dots.
Lots of other stuff, right? So two shapes, right? Two shapes can intersect. Two circles intersect. How many points do they intersect at?
2.
Two of them. One and two of them. If I draw this line, that line contains those 2 points. But does that line accurately describe the intersection of those two circles?
No.
No.
It's got a whole lot.
No, it does. A whole lot more of them. So what do we need to do?
Parameterize.
We need to narrow down that set. Like all the points we know, all the points we find will abide by this rule, correct? But we need to take away a whole lot of them. We can get an idea of what this looks like if we actually made a graph, which you can. First of all, what does z equal the square root of x squared plus y squared look like?
A cone.
It's a what? A what?
A cone.
A what?
Cone.
A cone, yes, a cone.
Yeah, that's what I know.
So when x and y are 0, what's z?
0.
It's 0, correct. So how do we figure out that it looks like a cone? Well, first of all, can z ever be negative? Oh, it says it's a cone. But how would we know it's a cone? I'm sorry, that's great. It actually knows it's a cone. That's cool. It's never negative. Why? Yeah, the principal root is always going to be positive. So if you look at each shadow like at a height, it's a circle. That's correct. So each shadow is a circle. So this thing goes up. It goes up. Kind of poorly drawn, but it's up like this. Like this. Like that. Okay, so we know it's a cone. Okay, that's cool. And it kind of looks like that. That's great. And that's a plane. Z equals 1 plus x. So does it matter what y is in this? No, it doesn't. So we know that this is x, and this is y, and this is z. So if y is 0, this thing crosses at what line? Z equals x plus 1. Z equals x plus 1. So let's say 1 is right there. Z equals x plus 1, so 1 and 1, so that would be negative 1, right? Actually, it's, excuse me, you have to be really careful about this, right? This is the positive, this is the positive, and this is the positive, right? So when x and y are 0, what's z? 1. Do you understand that? So that's why we have this point right there. That would be 1. What happens when z is 0? X is negative 1. So x is back here. I'm just trying to draw this as accurately as that's negative 1. So it's this line is that line of intersection on that plane, right? But then what does that line become? A surface, a plane, right? It goes out to the side. So this thing goes out like this. There's this plane right here. What does that plane do? It intersects the cone. So you have a cone that's getting cut, right? And the thing is this cone filled in?
No.
No, it's not. The cone is not filled in. So we're slicing this thing. Keep in mind it's going this way too. We're slicing this thing. What's the shape going to be? Do you remember what this shape is? Yeah, well, is it ever going to close? Well, look, you have this, right? And you're cutting off down like this, right? At an angle, right? So you have this as your intersection right there. And then it goes back around like this. Like there's your intersection, right? Do you see it's been cut off? Like if I took a sword and cut it off, right? So the intersection is that path. The intersection is this path. Is that an ellipse? What?
Wait, why does it stop? Doesn't the cone keep growing?
Yeah, it keeps going, keeps getting bigger. Right, exactly. That's why there are arrows on this. It keeps getting bigger, but for it to be an ellipse, it has to close. Does this thing close?
It's like a semi-ellipse.
We don't know for certain because if it stays parallel, here's the side of a cone, right? If we cut it parallel to the side of the cone, is it ever going to close?
No. But if
No.
It's not parallel, then it will.
But if it's not parallel, well, excuse me, if it's steeper this way, it'll eventually close. But what happens if it's steeper this way? You'll get some sort of maybe hyperabola, right? Maybe a parabola. I can't remember. You need conic sections. I haven't taught conic sections in a long, long time, so I don't know. So essentially, we need to narrow this down because it's not a plane. Did we do one like this? So what we found so far, just to recap, we know it's going to be look like it's going to be a parabola. We know the footprint at least is going to be a parabola. So we think that the actual curve is going to be a parabola. We did some substitution, and either way, direct substitution. Can square it out, you end up with the same thing. You end up with this right here. But we think that that's not the actual intersection. That's the shadow of the intersection. So does this ring any bells? We're close. I'll try to give you a page number and see if... So do we have x, y, and z now? Yeah, it's right there. That right there would be the equation in parametric form. So if we want the vector equation, how would we have to write it? What's one way we could write it? R of t is going to be equal to what? Negative? Why are we doing negative all of a sudden? 1/2. This is the x coordinate, right? T squared minus 1 times I plus tj plus, and this is glitching out for a sec. Sorry, I gotta get this down. Plus 1/2 t squared minus 1 plus 1, right? Times what? There it is. Is that pretty neat?
Way too easy.
No, hold up, but here's the thing. The method is easy. Seeing the method always
But
easy?
you really can just make one variable equal to t.
Why not?
Doable.
Is this relationship right here? This relationship right here is the exact same thing as this one.
Can we graph that?
It's the same set of points. No, we did. It's the parabola on the ground. This one moves, right? It's the same set of points, though, right? Can you make any point here appear over here? Yes. Any point over here occurs over here. Is that really kind of like the cheap way of parametricizing something? Sure. But then it allows us to then take this and pump out the z, which is what we really needed, right? We had x and y. We had the footprint, but we needed the height. Yay. We haven't really analyzed what direction it's going in, right? But we could if we wanted to, right? We could just plot a few points and go, oh, it goes from here to here. So it's, we good? Are there how many different ways can you parametricize a function or relation? There's an infinite number of ways to parametricize it, right? Basically, it's the same thing as how many different ways can you write one function as the composition of two functions? An infinite number of ways. I mean, we looked at this one, right? I asked you, or did I erase it? No, like if it's x to the fourth, it could be x squared composed of x squared, or x to the fourth composed with x, or x to the eighth composed with the square root of x, right? There's an infinite number of ways. So how many different ways can you parametricize a curve? Many. Is there generally probably a most straightforward method?
Yep.
Yeah. Danny, stand up. Could x be cosine if we wanted to? Sure. 5 sine t, y is equal to 5 cosine t. So what does that mean z is equal to? 25 sine t cosine t, correct? But we need a relationship of the intersection, right? We need a relationship. So for this one right here, what does z equals xy look like? Anybody know? Okay, so this one is a ball is thrown from the ground with the speed of 150 meters per second with an elevation angle. Find the angle of elevation that can be used to reach 800 meters away from the point where it was thrown. That's awesome. This is a fantastic question. Good job, Jay. Where is it?
There are 2 ends.
Awesome. Very good. So you want to try doing this one and see what happens? So let's just draw what's going on here. So we have the ground. This is a fantastic question. Man, I should write this into the test. Maybe next year. So this thing is fired. Do we have an idea? Everybody, you just said I don't like you in Korean, didn't you?
Yeah.
I speak Korean. Do we have any idea what theta is?
No.
No, but we know that the magnitude, the initial magnitude is 150. meters per second, right? And we know that this thing hits at, let's call this,
Delta X. Sorry.
well, hold up, we'll be fair, yeah. Shh, no physics. This is the origin, okay? And this is the landing spot. And we'll call this L. So we know that L has to equal 800. This is the x-axis. We'll call this the x-axis. 800i, yes. Excellent, 800i, awesome. Does this make sense? Does this make sense what it's asking? Now, the only way you hope that there's some angle it'll actually work. So I mean, can you fire an object arbitrarily far if gravity's in play? If I fire an object at an angle of 20 degrees, does it go arbitrarily far?
What do you mean arbitrary?
Yeah.
As far as you want?
Yes.
No, because gravity is pulling it down, so eventually what happens?
It hits the ground.
We live in a finite universe, right? Time passes, it'll hit the ground eventually, right? We just hope that it can get that far, right? Do we suspect it can get that far?
Yes.
We suspect we can get that far for two reasons. One, J-Hook is telling us so, or he thinks so, right? And also because, do you remember the questions we did before? The last question it asked for projectile motion, what's the speed at impact, right? And the speed at impact is the magnitude of the velocity at impact, right? And the magnitude, what have the magnitudes of impact been for the part of the projectiles we've been looking at?
500.
Like it still has some juice in it, right? It's not just going down. It has some horizontal. It had some horizontal momentum. It's always gonna have a little bit. Okay, so what do we need to come up with first? What was the first thing we came up with when we did these projectile motion questions?
Acceleration.
No. Okay, yes. We came up with two things. Fine. A of t is equal to, and we'll just say negative g of
J.
j.
Just curious, did you use 10 or negative 9.8?
We're just going to use negative g for now, okay? When we need to plug it in, we'll do it at the end, okay? A lot of things will cancel that way. Okay, so we did it, but what else did we find first? The velocity what? The velocity vector, right? The initial velocity vector. We want this, right? V of 0, right? When we did this before, what kinds of theta values did we use? We used...
20, 30.
No, we used 30 and
60.
60. Why did we use 30 and 60?
It's easy.
They're nice, right? They're nice. So now we have this triangle, right? And we don't know. The first thing we did was we found the direction vector, and we usually direction of v of v naught. We found like the if it was a unit vector, because we had like 1/2 ball, 150 meters per second, huh? We got a cannon, don't we? Really don't get in the way of that one, right? So look, we have this initial direction vector, and we know it's 150 sine theta times I, right? Plus what?
No, that'd be J. That's height.
Thank you. Thank you very much. Yes, that is J. Thank you. And then what's the horizontal going to be? Well, it's the other one. But again, is this necessarily a unit vector?
No.
No. So there it is, right? So we want it to go in that direction, but to have a magnitude of what?
150.
150, right? So we want to multiply by A on both of these, because whatever we multiply 1 by, we have to multiply the other. Let's not use A. That's a bad constant to choose. What constant should we use?
B.
Okay. So we want to multiply this, right, by B, so that the magnitude of this is equal to what?
150.
Why? Because what's the initial velocity?
150.
Exactly. So we want to go, listen, we want to go, and do you agree that this is the direction, the initial direction, right? Do you agree that its magnitude is not necessarily 150 and it's not necessarily 1?
Yeah.
We want the magnitude to be what?
150.
But we can't change the
Direction.
direction. This right here is the direction. So if we can't change the direction, what's the only thing we can do? Multiply by a
Scalar.
scalar, a constant, exactly. And we need that magnitude to be what?
150.
150. Fortunately, we're dealing with sines and cosines, so does our life get a little bit better?
Yeah.
What?
Yeah.
Because this is the way I want you to do it right now, okay?
But if we write it out in vector form, it should be magnitude is equal to
Yeah.
because
That's
that's
why I'm
the length
confused.
of
That's what you.
that's the length of
Oh.
Yeah.
So B equals 1.
Okay, ready? This is on the record. Ningi, you're right. I'm totally wrong. Although, yes, Chen is actually right. What is B equal to?
1.
Sorry, class. I was really excited because I understood really what was going on, and I did, but at the same time I did. It is recording now. So we've done this. We've solved for C2. We now have conclusively, we have the position function, right?
Set it equal to 800.
Can we just set this thing? This is a vector, right? It goes 800, right?
800 I.
The horizontal needs to be 800, right? So can someone tell me what, I'm doing that way too emphatically. Can someone tell me what needs to equal 800 here?
Horizontal component.
150 what? Cosine theta times t equals 800. So we have an issue here.
No, you want the height to be 0, don't you?
What?
Don't you want the height to be 0 when it?
Exactly. So listen, so we want that to be true, and what do we want to be true? 150.
With the same t.
It better be.
Yep.
If it's landing at 800, it better be, right? Sine theta t minus g over 2 t squared has to equal what?
0.
0. Which one do you want to look at first?
The first one is easy.
Let's look at the first one, right? So we have the first, really? Okay, it's fine. Doesn't matter, I guess. I guess they're good. So in this case, what does t equal on the first one? 800 over
150 cosine theta.
150 cosine theta. What can we do now?
Plug it in.
Plug it in.
Second
Plug it in, and now we're just in algebra fun land, right? So we have 150 sine theta, right? It's not that bad. It could be a lot worse. Times
800
over cosine theta, right?
Squared.
No.
No, not yet.
Not-
Minus g over 2 times 800 over
150
cosine theta squared, and that has to equal what?
0.
Equals, and now here's the thing. Can we factor something out of both of these? Yeah, please do that. So we know that we could factor out 800 over 150 cosine theta, correct? And we end up with 150 sine theta, right? Minus what?
G over 2 800.
G times, g over 2 times.
800 over 150 cosine theta.
Guys, can you, are you talking about math? Equals what? Because it's squared. There's still one of those left. Now, can this ever be 0?
No.
No. Why not?
Cosine can't.
Because
be
you can't make the
bigger than
denominator 0. There's no way to make just the numerator 0, right? So what do we can just go, oh, look, it's gone. In terms of our solving, right? So now we need to solve this. What should I do?
1. Calculator.
Yeah, ready? At this point, I don't see a super clever way to solve this nicely. Do you see a super clever way to solve this nicely?
Solve.
I don't. So ready?
Solve.
Calculator.
Hold on, I'm getting it. Right, 150
What do you get? In what?
In degree.
Shh, 79 point what? And this is degrees. Yeah. Now here's, can someone tell me why there's 2 answers? There's one answer where the particle goes up, down, right? And then there's another one where it goes boom, right?
Yeah, one has
You got like
further
a
time.
mortar and a
Like a mortar, or like, so if I take a baseball and I throw it really hard like this, and remember, there's no horizontal friction here, right? There's no horizontal friction at all. It's going to go up and then down, or it's going to go boom, like that. Absolutely.